as long as we're all clear on those ground rules, or if you have to miss class for another class, all that kind of stuff. So we'll see how this goes. I don't know exactly how I'm going to do it. My plan is, if the file's not too big, to have the TA posted on Blackboard after class, maybe set up some sort of private YouTube channel or something else that we could do. So we'll see how it goes. So exams, I have graded the first 2 problems. I'm on the just started the 3rd problem. So I grade 1 problem at a time to try to keep it as consistent as possible. So a couple advantages. I don't really know whose exam I'm grading because I'm just focusing on the problem. Second advantage is I'm hopefully then more consistent when I grade from across exams. So that's a bit of blocking for you, right? Come on. Okay, so we're going to continue on with what we've been doing before, which is chapter 6. And so we're talking about hypothesis testing. And then just maybe to review the procedure, these are the steps that we're going to do. So we define your null hypothesis and your alternative hypothesis, right? So we define H0 and H1, and we're using Greek letters for those things, so population parameters. And then the second step is we say whatever H0 is, whatever our null hypothesis is, we're going to assume that's true. And right now, we're looking at tests on mean. When we say assume H0 is true, that's going to put the distribution somewhere. Right? We're saying mu is equal to 12, or whatever it is. Then we go out and collect some data to test this hypothesis. And the data we're going to collect will be some x bar. And conceptually, if this x bar comes from the middle of this distribution, we'll say, yeah, it seems to be consistent with the null hypothesis. We don't prove the null hypothesis, but that doesn't refute it. But if this x bar then comes way out here in the tail somewhere, we'd say, boy, it's unlikely to calculate an x bar if mu really is 12. Therefore, we reject the null hypothesis and accept or prove the alternative hypothesis that way. So then the bit of vagary there when I say that distribution or x bar is in the tails, what do I mean by in the tails? And that just means, well, to put a number on it, we'll say if you get an x bar here, we're going to look at the area there and call that the p-value. And we'll just compare it to some area that is called the level of the test, or alpha. And generally, we use alpha as 5%. So if p is less than alpha, that means this area is less than our hurdle value for area. We would reject the null hypothesis. And so again, going down here, or up, down here where we're at. Okay, what I just said is that last step is the one way we can do it. We can compare p with alpha. Right? So if p is less than alpha, we reject the null hypothesis. Another way we could have done it is, all right, given an alpha, if alpha was 5%, we could say that corresponds to some hurdle value of t star. So alpha, we think of, that's a hurdle value based on area. Based on area. T star is the same thing, being a hurdle value based on t. So in the first step, we compare p with alpha. In this step, we are going to compare our t, right? And this is, both of these are our data give us t, our x bars. We can turn into a p-value or a t and compare them to hurdle values, which are alphas or t stars. And both of these ways of doing it are legitimate. The first one is just, we call the p-value method. The second one, we call that fixed level testing. and it's just a small variation. They're just slight variations of each other. Okay, so a couple things before we get going on some example and group problems is terminology. When we reject the null hypothesis, we say the thing is statistically significant. Right? So when you reject the null hypothesis, we saw a statistically significant effect happen. Now, the word significant doesn't mean important in this case. Statistically significant means there is a signal that's discernible from the noise. Right? So we have a strong signal-to-noise ratio. That's what we mean by statistically significant. There's an effect there that stands out from the noise. So it doesn't mean anybody's going to care about our results. So that's pretty important. And so this is a pretty good example of that. So in the book, it just says, all right, we've got this supplement, and we've done a test on a bunch of students and found that it improves scores on an exam, but it was highly statistically significant. So even at the 99% confidence level, or we would say that at the 1% alpha, so that would be alpha equals 1%. Even at that high level of evidence that we're requiring, we got a result, a signal that's discernible from the noise. But the true change in test scores isn't going to mean a whole lot to people. So if this thing is fairly expensive, those kind of things. So we would say it's probably not important, even though it was highly statistically significant. So as engineers, what part of our job is we really should match these two up. And that's what we'll do getting into the next section. One of the things that we're going to look at, or even coming up very soon, is how do we match these things up, right? So let's ask ourselves a question. How did we get, right? There's not much difference here, right, in the test scores, 85.2, 85.1. And you think about doing the experiment, what do you think they did to get such a statistically significant result? Which means here's our signal. Our signal is 85.2 minus 85.1. So a change in 0.1. That's a small signal, right? And so statistically significant means that signal stands up apart from what? The noise. So somehow, to get this so significant, they had to really, really reduce the noise. How do you think they did that? Yes, they probably had a huge number of data points, right? So then x bar, and we have sigma of x bar equal to sigma x over square root of n. So probably took a whole lot of data points. So one thing that you could say is, well, there's a couple things you could say. One thing that you could say that's a little bit strange to hear at first is you can make almost any result statistically significant if you take enough data points. If that thing is doing the slightest thing at all, as long as you take enough data points, you could say it's statistically significant, if it's doing something at all. Okay? So what we need to do as engineers is if an effect that's this size is important, and generally we're thinking sort of economically important, right? If this size of an effect is economically important, what we want to do is design our experiments so we will detect a signal this size. It will be discernible from the noise. If we take too much data points, we're looking for effects that are this small. And we'll find all of these, even though they don't really impact our bottom line. Does everyone see that? And then if we don't take enough data point, then an effect has to be like this big before we find it. And those are things that, well, they're so obvious because they're so giant anyway, we're probably not going to find something, we probably have already found those huge effects already. Does that make sense? So keep that in mind. We're going to hit this a lot of times. We get to choose generally how many data points we take. And that, by choosing how many data points we take, we are setting, okay, this many data points is going to probably show an effect, whatever size. And that's going to pop out as statistically significant. So we're trying to match that up. What becomes statistically significant should also be important to somebody, and try to get those as equal as possible. So we can, again, this is important, so I'm kind of beating it into the ground, but you can overdo it. You can take way too much data, and then you're finding all sorts of little effects that probably don't mean a lot economically. Or you can do it the other way, not take enough data, and then you're missing real effects. It all gets lost in the noise. So keep that in mind, that we're going to come back to that, and it's going to be probably one of the most difficult concepts in the class is when we talk about what I just said, that concept. And we're going to do some calculations based on how do we get the right amount of data. So important things are statistically significant, but unimportant things aren't. Okay, let's move on. So the first thing that we've done, and I admit we didn't do a whole lot of it, is we did this hypothesis test on means, right? We did mu equals whatever, and we got x bar, and we looked at large samples. And the nice thing about large samples was a couple things, that we don't really know sigma, but when we have a lot of data points, our sample size S, our sample standard deviation S, will approximate sigma very nicely, and x bar will be normally distributed. Two things that I thought you knew before the exam yesterday. So we'll talk about that later. So if we have enough data points, x bar is normally distributed. I would say half the class told me that if we took a lot of data, the data points themselves become normally distributed. That's not true. X bar becomes normally distributed. You can take more and more and more data. The data is distributed the same way. All right. So now, when we get to a small sample size, what happens? A couple things happens. We're not so sure about this. S approximates sigma not so well, so that's where we use a t-distribution. Right? So a t-distribution, we're penalizing ourselves for not knowing sigma very well. So the number of degrees of freedom will dial in, how confident we are in this. And then because we can't be so sure that x bar is normally distributed, we need to take a look at half normal plots or normal probability plots of the individual data points. And we have to assume that they are fairly normally distributed. So the t-distribution is the same as it was before. Okay, let me. Okay. And then also, we have one-sided tests and two-sided tests. For one-sided tests, we look to our alternative hypothesis. If it's just greater or less than, then our p-value only comes from one tail. If the alternative hypothesis is it doesn't equal, then we refute the null hypothesis for really big values of x bar, really small values of x bar. So we're looking in both tails for our p-value. So we should do an example here before we get too far along. Any questions before we do this example? I think examples tend to clear things up a lot. All right, so take a minute to read that, please. All right, everybody okay? Understand what we're doing? First step is to set up our null and alternative hypothesis. And now we're saying this is based on mu, the population mean pH. Sort of you could think of it as what's the true pH value of this stuff. So now we have some choice here. And this is where it can be a little bit tricky. And I think it's easier to keep in mind what those two hypotheses are set up. So let's think about, we're wondering if we can conclude that the mean pH is less than 7. Okay, so if we want to, or if we want to conclude the pH is less than 7, the only way we can do that is by disproving that the pH is greater than 7. Another way to say that is these questions of can you say yes to this question generally clue you in on that's H1. So our null hypothesis is that the mean is less than 7. So the only way that we can do that is by disproving the null hypothesis, that mean is greater than or equal to 7. Okay, so let me do this over here. So the second step is we assume the null hypothesis is true. Assuming the null hypothesis is true says the mean is greater than or equal to 7. So I'm going to put it right at 7 because that would be, you could think of the worst case scenario or the toughest case to disprove. So that sets the mean at 7. Is everyone okay with that? Okay, so then to disprove the null hypothesis, what do we have? We would get results that are out here, right? The mean is less than 7. And so another way to look at your alternative hypothesis is you could look at your data and say, what do your data seem to indicate? We got an X bar is 6.68. So, I just drew that distribution. Is this 6.68, is it way far in the tails or is it in the middle? We don't really know, right? So we have to get a number to figure that out. So we need to need to get that X bar into a T and that into a p-value. And then we're going to compare it with our hurdle rate based on area. And then we'll say, how does that compare with alpha? So T. T equals X bar minus mu over that's the noise in, maybe I'll back up one step and do it that way. X bar minus mu naught over Sx over the square root of n. So 6.68 minus 7.0, and S was what? 0.2? 6. So I got that to be minus 3.919. Almost, again, what is T value? T tells us it's a signal to noise ratio. It also tells us how many standard deviations we are away from the mean. So practically speaking, if you're about 4 standard deviations away from the mean, is that a long way? Are you out in the tails or are you in the middle? Way out in the tails. So our p-value is going to be real small. And so you look it up in your book, you can't find that particular number. Why don't you pull out your t-tables in your book? And you can't find that particular number, but you can find 2 numbers around it. Right? You can find minus 3.365. And so we're looking at 5 degrees of freedom. we can look at that t-value, and it gives an area of 1%. We can find the area on the other side, and it gives an area of 0.5%. So our p-value is going to be between 0.5 and 1%, right? Because that's the one we're looking at there. So again, the ones I circled in red, those are the ones we can find in our book that correspond to 1% and 0.5%, and we're somewhere in the middle. So our p-value is between 0.5 and 1%, which means we compare that to our hurdle area value alpha, which is 5%. So in this case, p is less than alpha, so then we would reject h0 and accept h1. And so that would say the pH is less than 7.0. Chris, you got a question?
Are there any famous examples of someone doing a statistics test against a population control, and the actual result wasn't what he thought it was, but that's just saying he got 99% sure it was correct, but it was more, there was that small chance.
Oh, good question. Are there any great examples of where things are statistically significant and don't turn out to be true? It's hard to, there are a lot of examples of that. It's hard to tell if it was because it was just that 1% that was the type 1 error, is what it's called, or if they did something wrong on their experiment. The only way we can tell that is if when someone else tries to replicate the experiment and it doesn't happen. And so it's hard for us to really get at exactly what was wrong with that. But there are lots of those examples, and that was that article that I sent out before where almost 2/3 of all this social science and psychological science research could not be replicated. And they were trying to, well, it was top journal, so I imagine they were requiring some statistics. But because there's so many ways you can mess up an experiment, you can still be wrong. But we'll talk about those very errors that you're mentioning. Okay, going the wrong way. Does that make sense, everyone? So now let's back up, and this was the p-value method where we went from x bar, our data, to get a t based on data that got a p-value, which was area from the data, and we compared it with the hurdle value of alpha. What if we did the fixed level testing way? How would we do that? It's very similar. The fixed level test would be first, we use alpha. So if my alpha was 5%, that corresponds to some hurdle value of t star. So someone look that up. We have 5 degrees of freedom. We want 5% in the tails. Our hurdle value for t now is what? I didn't do it this way, so I'm wondering what you got. Pardon? 2.015. 2.015. Anyone else? Everyone get that? So then what we do is we have our t-value compared of our data, and if our t-value is further out in the tails than our hurdle value, we reject h0 and accept h1. So just think, p-value and alpha, you're comparing your area from your data with your hurdle alpha. Now you're comparing your t from your data with a hurdle value of t star that really came from alpha, one step. Does that make sense at all? So if you're doing a lot of these tests, you might do this fixed level testing way, where you might find your t star hurdle value, and then that just saves on calculations, because you don't have to go and look up all these different p-values. You just calculate your t's from your data. All right, two ways of getting to the same conclusion, and they're very small differences. All right, so why don't we do this group problem? And by we, I mean you. Make sure you go through all the steps. Define your null hypothesis, your alternative hypothesis. Assume H naught is true, and then draw the distribution. Put in your X bar, shade your area, figure if it's one or two-sided, all that business. All right. If you have questions, let me know. Talk to people around you, if you have someone around you. You'll have to yell at Katie Vaughn. Those people watching the video better be doing the problem now and not fast forwarding it. If any of you guys see anybody do that, you let me know. Spy on them.
What you should do, Professor, just rant on for 30 more minutes and then see how many times they skip through. While we get through that.
I might not want to know the results of that. Okay, any questions about things? You can do that. Okay. Anyone having problems with the hypothesis, putting that down? For part A, the only way we could conclude the mean concentration is greater than 20 is by disproving the null hypothesis. Right? So this is a clue that that's H1. So sometimes it's easier to write H1 down first. The mean is greater than 20. And the only way we can disprove that is by rejecting the null hypothesis that the mean is less than 20. For part A, let's do this the p-value way. For part B, do that with the fixed level testing. Right? So that T star business. In both cases, I don't think it tells you, let's make it a 5% level test. Does it say? I don't think it does. Is on B already? paperless today. You're very green. You're very earth conscious today. How's it going, Steve? All right. You guys are done already with both A and B? All right. All right, let's go over, should we go over A now? Probably could do both. Okay, for part A, I've defined the null hypothesis and the alternative hypothesis. The next step is I assume the null hypothesis is true. And that means mu equals 20. So that's the next step. Then after that, I go out and get some data. And here, let's see, what do we got? We went out and took data, 26 data points. The x bar of those is 20.75, and S is that. And so I said, well, I got an x bar is 20.75. And now the next step after that is to figure out, well, does that x bar agree with mu equals 20 or disagree? Means, is x bar from the middle of the distribution, which seems to go in line with our null hypothesis, or is it out in the tails? And so for part A, to figure out if we're out in the tails or not, we're going to do this p-value method. So we're going to try to figure out, well, what is that p-value? And we're going to compare it with the 5% value. So to get this p-value, I need to convert this x bar into a t. Not quite a z, because we're not quite at 30, but we want a t there. So x bar minus mu over the standard deviation of x bar, which is individual measurements over n. So 20.75 minus 20 over 3.93, square root of 26. I got 0.973. So is that in the middle or in the tails? Or less than one standard deviation of the way? Probably in the middle-ish. So the area, so that corresponds to a p-value of 0.17. In your book, you probably couldn't find t of 0.973 and 25 degrees of freedom, right? So you have to bracket it. How I got this is I just wanted to show in Excel, you can use, this is the old function tdist. I think it's still supported. And I gave, here's my t value, how many degrees of freedom, and I put and then it's 1 or 2 tailed. So 1 is area in 1 tail, and it returned 0.17. So it's a one-sided test, right? Only a one-sided test means only high values of x bar will disprove our null hypothesis. That's why it's one-sided or one-tailed. So our conclusion is we fail to reject the null hypothesis. And so we could say, we would have to say, we cannot conclude. That the mean is greater than 20. I'll write that down. Any questions on part A? Part B, yeah, Andreas.
P-values, are they normally presented as a decimal or can they also be presented as a percent?
Decimal, percent, either way, just different units. I guess I've seen them both interchangeable. Yeah, Chris.
So the probability that less than 20 was 17%.
Good question. We would say,
According to this test, right?
I understand what you're saying, but I just take issue with the word probability. So,
Looking at the time where P stands.
yeah, we use the word plausibility. So that describes the plausibility of the null hypothesis. This is a detail that nobody has to know. If this is confusing it at all, then just forget it. I hesitate to even say. Why I took issue with the word probability is something that we use to describe some random event, some outcome some experiment we don't know the outcome to, right? But mu is the population mean, so it either is or isn't less than 20. It doesn't change. So we don't talk about probabilities with that. But that's really a detail. So we just talk about plausibility of the null hypothesis. Oh. Yes, it has to be 0.05 or lower for us to say that's enough evidence to reject the null hypothesis. And keep in mind, and that's arbitrary. We pick 5% just because most people, it works. But for different situations as an engineer, you might need more evidence or less. So you have to balance, well, what are the costs of making these errors? And we're going to talk about that in a little bit. So for part B, did you guys have any problems? Does the fixed level testing seem much stranger to you? Anybody get answers for part B yet? Some? All right, why don't everybody work through part B. Just give you a few more minutes on it. And so now what you want to do is find a t star, a hurdle value for t, and compare the t from your data with the t star, which is a hurdle value for it. What'd you guys get for T? T star? T. Okay, great. That's, at least I got the T. I didn't do the T star. How you doing, Bob? Okay, so all the steps are the same except for that very end. So instead of going from T to a T star, or I'm sorry, instead of going from T to P value, we go alpha to a T star, and so we compare the T star with that.
Okay, and how, I guess I'm still a little confused because I wasn't fully getting the
Oh, okay. Okay, so you want to find, that's a good question. So you have, what do we have, 25 degrees of freedom here? So at 25 degrees of freedom, we want to find, okay, here's the area, and then here are the T values. And so we had 0.9. So for us, we say, okay, that was between these two areas, 0.25 and 0.1. And so I got it more exactly on Excel, but for you, you just say, oh, it's somewhere between 10 and 25%. Either way, it's really high. And so, okay, good. Yeah, I should have used the book probably. got part B done. All right, let's go over part B. So we're going to do it the fixed level test way. So again, we need to define null hypothesis, alternative hypothesis. This tips us off that we can use that for say hello, H1. So if that's H1, the mean is less than 25, then the alternative hypothesis is the other side of that. I'm sorry, the null hypothesis is. Then we assume H naught. So when I say assume H naught, I mean assume H naught is true. The mean really is 25, maybe less, but 25 will be the case that we test because it's the worst case scenario. And we have these same data here. Sort of worked. Okay. So we have the same data there. Okay. So X bar was 20.75, and we're wondering, okay, we're wondering if that's in the tails or not. Oh, I did such a bad job drawing this. X bar is 20.75. Now the fixed level testing, again, from the p-value method, we took that 20.75 and we got the area. We got area out of that. But now what we're going to do is we're going to start with alpha and get a t star. So in the fixed level, we said, well, if alpha is 5%, I can get a t star value right there, which is what? So t star with 25 degrees of freedom, 0.05. Anyone get something for me there? 1.708. Does everyone get that? If not, look up where that is. And so now, to do our test, we're going to compare the t that we got to this value. If the t that we got is further out in the tails, so by 1.78, it's going to be plus or minus. So if we get a t value that's more negative than this, or anywhere out here, then we will reject the null hypothesis. So that is called the rejection region. And it's the region, if I get a t out there, then I reject the null hypothesis. So my t value is 20.75, x bar minus mu, over S of x bar. And that ends up being what? Minus 5.51. So now I compare these two values. The t from my data is way further out in the tails than the hurdle value, right? Yeah, Mark.
Is that t star value negative just because we're going backwards?
Yeah, yes, it's negative because we're looking on the left side of the distribution. Does everyone see where the t value for our data set is 5.5 standard deviations away from the mean, and our hurdle value is saying if it was more than 1.7 standard deviations from the mean, we would reject the null hypothesis. So that would be the fixed level way of saying we reject the null hypothesis. Yes?
So I converted both to p-values and figured it out that way, or you like gave up?
Oh, okay. So you could do this the p-value method and get the same conclusion. Just be able to do both ways. I might specify, use the fixed level way, use p-value way. And I mean that way because it's a different way of thinking that sort of each has its place. The p-value way is the way you generally go about doing this and reporting data. The fixed level way helps us understand one of the most difficult concepts in the class. So that's why I'm starting to do a little bit more fixed level stuff here. Okay, yeah, Sean.
So when we write an earlier for this, when we do the fixed level test, if we say that T star is greater than T, we can say that H naught can be H proven.
Right, we would say if our T, so we would say if our negative T is less than negative T star, if it's further in the left-hand tail, which is this case, right, then we reject the null hypothesis. So I don't like to throw in these negative things, in essence. I just think of it, is the T from our data further in the tails than the T star? So it's a little bit, you could use absolute values in there, and it's fine as well, but I just like to compare it, think about what distribution we're on, and then say that tells us we reject the null hypothesis and accept H1. So H1 says, yes, the mean is less than 25. Right? We say we have proven this to be true. Does everyone see why we call this the rejection region? Because if our data, if our T falls in that region, then we reject the null hypothesis. Are you sure you don't have questions? All right. Okay, so concept-wise, the nice thing is we're going to go through we're going to kind of slug through all the same cases that we did with confidence levels, but it will help cement the same procedure. It's just sort of a different calculation where we've done hypothesis tests on means, large sample, small sample. Now we'll go to the next stage and say, well, let's look at the difference between two means, and we'll do large samples and we'll do small samples, but we're going to keep going through this same methodology, the same steps. So hopefully this will sort of settle in now. So just like we did with confidence intervals, let's start thinking about, we would very often like to compare two means. Here's a mean with a treatment, here's a mean without a treatment. Are they different? Is one bigger than the other? And we would like to test that at the whatever 5% level or 1% level, whatever the case may be. So we're going to do the same steps. We're going to have a null hypothesis and an alternative hypothesis. Our null hypothesis is generally going to be, well, mu of this data set is the same as y. And the alternative could be one-sided or two-sided. If it's two-sided, we'd say it's not equal to y. And I would say the first few times you do this, write it like that, because it's very clear those are my null and alternative hypotheses. We can really grab onto those. But to do the test, we will just do some mathematical trickery and say mu x minus mu y equals 0. And we'd say mu x minus mu y does not equal 0. I just moved the mu y over to the other side of the equation. Subtracted mu y from both sides, right? Because this gives us a number we can test. And again, we can think of this as defining a new random variable if we want. So this says if the next step would be assume H naught is true, which would place this distribution. So mu x minus mu y is equal to 0. Is everyone okay with that? That's by far the standard case we could do. But we could, and this is getting back here, I want to tie this into the notes. Instead of thinking the mean of x is the same as the mean of y, we could say that the two means don't differ by some number, say 2 or 3. Right? So it doesn't necessarily have to be 0. We could put any number there we wanted to and test that, that hypothesis. So the general case, this is some hypothesized difference right here. The difference between x and y is less than the value of 2. But very often, almost always, that hypothesized difference is going to be 0. OK. Is everyone OK with that? So that's where now we've got large samples. So we compute a z-score, which again, z is something minus the mu of that thing divided by the noise of that thing. And the thing we're talking about is a difference between two means. This is the same equation that we used for confidence intervals, just rearranged. So in our case, above here, we would say z would be x bar minus y bar minus 0, which is our hypothesized difference, over the noise and the difference between two means. And we did that before. Linear combination of random variables. This guy right here is sigma of x bar. This is sigma of y bar. And we express them in terms of the standard deviations of the individual measurements that we can get at. And then all the rest of this, once you have a z, then the other steps are the same. Either you go you go from z to get a p-value and compare p to alpha, or you use alpha to get a z star and compare z to z star. All right, so let's look at this example. All right, take a minute, read through this. And instead of an example, why don't we do this as a group problem? I think it's worth slowing down a little bit and having you guys do more of the stuff in class. Make sure you're doing all the steps. Write down your null hypothesis, alternative hypothesis based on population parameters, which would be mu x and mu y, or mu a and mu b, whatever you want to do. Assume the null hypothesis is true. Then calculate the statistic of interest. Get its z-score. And then either get a p-value and compare to alpha, or go from alpha to get a p z star and compare z. Yeah, Chris.
Just like this specific example would be very easy to get a lot of samples, so you could make n very large.
This particular experiment, yeah, they did. I think they did a lot. Yes, they did get a lot of them. So, yeah, go ahead.
This type happens to be one problem you can take a lot from.
Yes, yeah, and that's a good point. Some experiments are really, really expensive, and we have to be okay with a few data points. And then some experiments, the data comes in large bunches, and it's easier for us to do that. Actually, now's as good a time as any. No, I'll wait till later. That'll be more of a cliffhanger. I've got a fun story. I've got several fun stories of crazy things my graduate students did in the lab. No, I'm going to wait till later to tell it. So. I don't want to spoil the story. It fits better in the next section of notes, I just realized. Any questions? How you doing, Mario? Question? No? Is it a one-sided or two-sided test? Two-sided, right? We've got this does not equal here, which means we reject a null hypothesis if our data is too big or too small, if y bar minus x bar is really big or really small. Did you get a z value of 1.97? And that's really close to 1.96. We know 1.96 corresponds to 5%. So our p-value is just slightly less than 5%. So here it's very, very close whether we would reject the null hypothesis or not. Right? It's right on the line. It's slightly over the line, so we'd slightly reject the null hypothesis, but just barely. And so the answer to this would be, oh, we did reject it. Yes, we can conclude that they're different. Yeah?
For these problems, are we just going to do a 5% level test on some candidates?
Good question. Yeah. The answer is, if it doesn't tell you, assume alpha is 5%, or so a 5% level, unless specified otherwise. And that'll be pretty much across the board in the class. On an exam, you can always ask me, and I'll tell you. I generally try to specify just to make it clear. But on homework, assume 5%. Any questions on that? Okay, so last concept that I'll say now, and then we'll rehash later, is if we do this fixed level testing, say, and or any level testing, if we're doing a 5% level testing, and we do a lot of these tests, let's say you do 100 of these tests, and they're all tests at the 5% level, how many times, we will reject the null hypothesis if our p-value is less than 5%, right? Should start there. Okay, sometimes, that means sometimes we will reject the null hypothesis because we got a small p-value simply by chance. Sometimes the null hypothesis will really be there, and we will get, we will get an X bar in one of those two regions, right? And if we get an X bar, we're going to say null hypothesis is rejected. And if alpha is 5%, 5% of the time that will happen, right? But that's the wrong conclusion. So 5% of the time, H naught is true, but we rejected it. And that'll happen 5% of the time if we're doing these 5% level tests. Does everyone see that? Mu really is at this point here, but simply due to random noise, we got an X bar that's out here in the tails. And then we reject the null hypothesis. We have no way of knowing it was due to random noise or what, but we rejected the null hypothesis, and we got the wrong, we did everything correctly, but our conclusion is not true. Yeah, Chris.
Is the null hypothesis true in that case, or just probable?
I'm saying if the null hypothesis is true, that's the starting point. If the null hypothesis is true, mu really is there, 5% of the time we will wrongly reject it. So that's one mistake we can make. HO is true, but we reject it. Now think, what other mistake can I make? Just think in these, look at that sentence. HO is true, but we rejected it. If you flip those around, what's another mistake that we can make? I think you said, I think if, in terms of H naught, I think you,
H naught is false, but we fail to reject it.
right. H naught is false, but we don't reject it. So what we're doing in statistics is we're trying to balance these two mistakes. And we're going to get really close to, we're going to put some numbers to these statements. And we're going to call this type 1 error, sometimes called alpha error. Why would you think it's called alpha error? Why would you think it is called alpha error? Yeah. Yes, because alpha tells you how often this happens. And then this one is called type 2 error. And then we just say it's beta error. And what our job will be in designing experiments is to balance these two mistakes. We can go wrong by having too big of an alpha error or too big of a beta error. And so we're going to try to design our experiments so that we are comfortable with both alpha and beta errors, which you'll find out is the same thing as what I said. If an effect is this big and we want to determine n to find effects that are that big and not way too small or way too big, it's the same thing as balancing alpha and beta error. But I'm going to end 6 minutes now early. I know. Well, we'll go 6 minutes late some other time. So, all right. Have a good day. Thanks for coming, and see you Wednesday.